Is it recording? No, no, that sounds right.
Yeah, I guess.
Okay. Well, maybe I will then. I'm going to share the screen, which I think it means you won't be able to see me, but maybe you're happy enough to see me. But hopefully you'll still hear me. So I'm going to try. Let's see if this works. Share the screen. Okay. Okay, I think I'm sharing the screen. You probably see. Do you see my desktop with lots of icons on it now?
Yeah, we can see it.
So I was going to have a little chat about these guys. I don't know if you can see the image here. Can you see the shape? I took something from online here. These are the platonic solids. You guys have probably heard of these, right? Can you see the image?
Yeah, we can see it.
Yeah. So what I might just draw something here, but essentially what I'm drawing here are, of course, this is the tetrahedron. Okay, so this is, of course, made up of four triangular pieces, equilateral triangles, right? So you can see them there. There's one there at the back. There's one, and there's one, and there's another at the back there. Okay, everyone happy with that? And then, of course, you have the cube that you all know. This, of course, is made up of 6 squares. And I won't write them all down or draw them all, but you also have the octahedron, which is made up of 8. Sorry, I can't seem to draw on this. I'm using the surface is glass, and it's kind of slippy, and my pen slips, so my writing is maybe difficult to read. There's also the dodecahedron, and this consists of 12 triangles. Sorry, not 12. I beg your pardon. Sorry, 12 pentagons. So pentagons like this. And finally, there's the icosahedron, which is 20 triangles. And I'll go back and we'll look at the pictures again. So if I go back up to the graphic here, hopefully you can see. So the writing is a little blurred, but of course this is my tetrahedron, my cube, my octahedron, my dodecahedron, and my icosahedron. So I mean, these words come from Greek, and the tetra here, of course, meaning 4, and the cube, actually it's a hexahedron or something, which is 6, but we usually just call it a cube. The octa meaning 8, dodeca meaning 12, icosa meaning 20. So these are from Greek words. Have you guys heard of these shapes? You've seen these before?
Not all of them, but yeah.
So there's something special about these 5 shapes. Do any of you know what's special about them? You can see here, by the way, with the dodecahedron, I have the faces are pentagons. Right, so all of these angles should be the same, by the way. My picture may not be very good, but all these angles are the same. And all of the side lengths, all of these side lengths are the same. Hang on, sorry. All of these sides are the same. And so on. Same with all of them. So anyone want to tell me what you think is special about these shapes? This shape is nothing but triangular face. This guy over here face square. Right? Here he faces a triangle. Here he faces a pentagon. So these shapes are built out of faces of two-dimensional shapes.
Mark, I guess your voice is not clear.
Let's stop. Can you hear me now?
Yeah, I can hear you right now.
Okay. Please tell me if you cannot hear me. So these are built out of two-dimensional pieces. Okay. So maybe if I go back here again for a second, you can see the cube here is built out of 6 squares, and we build this by putting the squares together. 6 squares. Does that make sense?
Yes, that makes sense.
Okay. So the question is, all right, here's a problem. Okay. If you take a two-dimensional polygon, so something like this, okay, so this is just a two-dimensional flat shape, okay, and we want it to be a regular polygon. So regular, that means all of the sides are the same length. So all sides same length, all angles the same. Okay, so also the angles here, all of the angles are the same. So that's going to be a regular polygon. Does that make sense, first of all? Everyone happy with that definition of a regular polygon?
Yes.
Okay. So for example, an equilateral triangle. Okay, so each of these sides being the same. Equilateral triangle, that works, yes. But a triangle like this, no. This would not work. Okay? Yeah. Square. Yes, that works. But something like that, no. Does that make sense? So this is regular. This is regular. These guys are not. Everyone happy with that?
Yes.
Great. Thanks, Liam. I'm sorry. I just need people to tell me so my voice is clear. And so on. You get a regular pentagon. And again, these angles are all the same. All the same. By the way, what angle is this?
Acute or obtuse.
Yeah, but does anybody know what the actual angle might be?
Maybe 45.
No, it's bigger than that. It's even bigger than 90 degrees, in fact.
108.
It's 108. Yeah, well done. 108 degrees. Yeah. How did you know that?
3 times 180 divided by 5.
Exactly. So do the rest of you understand what he did? You can always break this shape into triangles, right? Yeah. So there's 3 triangles, right? And each of the triangles has angles adding up to 180 degrees. So you get 180 degrees plus 180 degrees plus 180 degrees, right? And what's that? That's equal to 540. But then there are 5 equal angles. So 540 degrees divided by 5 is 108 degrees. Thank you for that. Okay, everyone happy so far?
Yes.
Yeah. So let's look at a hexagon. So a regular hexagon, right? So this is, again, all of these angles will be the same. And of course, to work out the angle here, you're going to be able, this can be broken up into how many triangles? Into 4 triangles. Sorry, I'll use a different color. 2, 3. So you get 4 triangles. So now you get 4 times 180 divided by, and we have 6 angles divided by 6. Okay, so 4 times 180, that's what? 720, right? And 720 divided by 6, that's equal to what? 120, right? So these are angles of 120 degrees. Okay, see how this works?
Yes.
Okay, so in general, if you have a polygon of any kind, even if it's not regular, let's just say n sides, you can always break this up into triangles, and you'll get n minus 2 triangles. Does that make sense?
Yes.
And so you can derive a general formula. So regular n-sided polygon has angle n minus 2 triangles times 180 degrees divided by, and you'll have n angles. So that's the formula for the angle. Okay, everyone happy with that?
Yes.
Again, so regular is the case when all the angles are the same. You can have polygons that, you know, don't have all the angles the same, but that would be the case if you have all the angles the same. Okay, so now let's talk about the solids. Okay, so question: how many regular solids can we build from these regular polygons? So I'll have to explain here what I mean by regular solid. There's another name for this: regular polyhedra. That's the fancy name. But so before we try to answer the question, let's just consider an example. So let's say the polygon is the square. So square. So we know we can build a cube, right? So we just need 6 of these. 6. So 6 of these, and we can put them together and we can build ourselves a cube, right? Notice that the angle here is, of course, 90 degrees. And notice that at each of these points, these points are called vertices. This is a vertex or a corner. Vertex. You can see that there are 3 squares meeting. Okay, 3 squares meet. Notice this is the same everywhere, right? If you take any other vertex, you always have three squares meeting, and the angles are always the same. So you can see the symmetry here. You always have this symmetry. You have the same number of angles, the same size meeting at every single vertex. The faces are all the same. They're all squares. So this is what I mean by regular, okay? The symmetry. Does that example make sense?
Yes.
Yeah, okay. Everyone else is happy with that? Great. Okay. So what else could we build with a square? Can we build any other? So anything else? Anything else? Can you build another regular solid or regular polyhedron from a square? What do you think?
Maybe like a square pyramids.
Well, so what do you mean by square pyramid? You mean a square on the base?
Yeah.
Like this, and then you mean sort of all of the pieces going up like that? Is that what you mean?
Yeah, but that's not regular, right?
Yeah, it's not regular because you don't have all the faces the same, right? You have a square down here, and then you have triangles here. So no,
yeah, that's true.
Not regular. So you're only allowed to use the one kind of face, right? The square face. Well, the answer is actually no, you can't. So answer, no. Only regular, solid, built from the square is the cube. So it turns out now, the big question is, how would you prove that? Right? That's a very good question. We're going to come back to that. But do you at least understand the question and answer? Yeah. So I'll leave you to think for a few minutes about why it's not possible to build one of these things from squares. Okay. Now let's consider the triangle. So here's another example. Triangle. So we have, from this we can build a tetrahedron. You put the triangle on the, you make the triangle a base, like, I can't draw. Make the triangle a base like this, and then you build up the other parts. So you have 4 triangles. So 4 of these. These are equilateral triangles, remember, okay? So all of these angles are the same. And so you put 4 of them together like that. That's the back. And you build this tetrahedron. Does everyone understand my picture?
Yes.
Great, okay. What else can I build from a triangle? Well, you might remember earlier, there's another example. So what I can do is the following. So I can use your idea, Liam, of a square-based pyramid, right? And this is going to have 4 triangles. Maybe I'll do the triangles in green. Sorry, I'll do this a little bit better. Hopefully you can see there are actually 4. It's hard to draw on this thing. There are 4 triangles here. Right, so just to be clear, that's one triangle at the front. There's another triangle here at the side. And there's another triangle here, and then there's one at the back. Can everyone see the 4 triangles?
Yeah, we can see it.
Great, great. So now we all agree that's not regular, yes? But what if I take 2 of them? So if I take another one underneath and stick it on the bottom, like that. Okay, so now I have a vertex here, a vertex here, a vertex here, a vertex here, a vertex there, and a vertex there. And so now hopefully you can see I have something which is regular, and it has 8 triangles. Sorry, but my writing is getting very bad. Triangles. Does that make sense? Okay.
Yes.
8 triangles. So this is called an octohedron or octahedron. And if we go back, I'll just go back up for a second to the very top where I had this image. Hold on. So now you see the 2 pieces we've talked about. There's the tetrahedron there. There's the octahedron here. And there's a third one, which I won't try to draw. It would take me too long to draw, but this is the icosahedron. And this one here, so hopefully you can see you have lots of triangles here. Lots of triangles. This has 20 triangles, 20 faces. Okay, so 20 triangles. Okay. So it is a fact, and something I will attempt to prove to you, although I may not get everything done today. But it is an interesting fact. So there's only 3 of these. So one more icosahedron. So exactly, this has 20 triangles. Exactly 3 possibilities. Okay. So just to go back, you can see with the square here, with the square, there was only one solid we could build, the cube. With the triangle, there are 3 possibilities: the tetrahedron, the octahedron, and also the icosahedron. Okay, I'm going to stop for a second. Is this making sense?
Yeah, it's all clear.
It's all clear. Okay. Let me go back up to the picture at the very start. Okay. Go back to the picture at the very, very start. I said there was something special about these shapes. So we see we've dealt with 4 of them now. There's the cube. That's the only shape you can build out of squares. That's regular. Okay. The only regular one you can build out of squares. You can build lots of other things out of squares, but not regular shapes, not regular solids. And this one, and this one are the only ones that can be built out of triangles. So that deals with that's the question for triangles and for squares. The next regular polygon is the pentagon, right? So this is 3-sided, 4-sided, 5-sided. And we see there's an example for the pentagon, and it's here. This is the so-called dodecahedron. Okay, I'll write the full name here: dodecahedron. And this is made up of 12 pentagons. Okay, you can see them all being glued together. It looks a little bit like a football. Okay, so being attached like that. Okay, and the question you can naturally ask is, are there any other shapes you can build using the pentagon? And the answer is no. This is the only one for the pentagon. Okay, that's it. So for the square, we get precisely the cube. For the triangle, we get these 3 here. We get those ones. And for the pentagon, we get exactly that. Okay. So just to be clear, sorry, 3 solids, 1 solid, that's the cube, and 1 solid. And the next question then is, well, what about the hexagon? Sorry, made a mistake. So that's the six-sided hexagon. What do you think? Do you think you can build anything using the hexagon that's regular? What would you guess, given the picture I've drawn? You guys are still there?
Yeah, we are. I'm not sure. Maybe
Just
we
checking
can't
you're there.
do anything with that shape.
Yeah, when you're correct. Sorry, I've lost my. Just a second. I lost the. Where is it? Here it is. Yeah, you're correct. And the answer is nothing. You cannot do anything with the hexagon. Zero. And in fact, if you take any larger polygon, so the next one up will be the septagon, which would have 1, 2, 3, 4, 5, 6. Sorry, I'm missing a side. Very hard to draw quickly. That's what I want to draw, something like this. So this is 7. And again, it's 0, no solids. And this pattern keeps going. You cannot build any regular, it goes on and on and on. It's all 0, 0, 0, nothing else. So the only polygons that you can build solids out of that are regular are the first 3, these ones, the triangle, the square, and the pentagon. And these 5 are precisely what you get. These are the so-called platonic solids. I'll write down the word. Platonic solids. And there are 5 of them. And this has been known for many thousands of years, that there are exactly 5 of these shapes. This is named after Plato. So Plato, the Greek philosopher. But these were known before Plato. I'm not quite sure why Plato is named there. I know he was very interested in them. But these have been known for thousands of years. And we know that there are precisely 5 of these and no others. So the interesting question is, we know now that there are 5 of them, but how do we know that there are no other shapes you can make? So how do we know this is 0? How do we know this is 0, and so on? How do we know these are the only ones here, that there aren't other ways we can make these things? So that's, I think, an interesting question. What do you think? Do you think it's an interesting question?
Yeah, it is.
You're not just saying that to be nice to me, are you?
No, it is like we have infinite sides, and we can determine if we can make solids from them or not.
Exactly. So that's a question I want to study with you. Now, I don't have probably as much time as I need to get through everything today. So I think what I'm going to do is split this into two sessions, if that's okay. We'll do some of this today and some of this next week. Is that okay with people?
Yeah, that would be great.
Yeah, that's fine. So I'm going to say a little bit more about this problem, and I'm going to teach. I'm going to show you why it's the case, and I'm going to teach you some interesting things along the way. Now, there are several proofs of this fact, and if you go online, you can probably find different proofs of the fact. And the proof I'm going to share with you is probably not the shortest one, but I think it's interesting because on the journey going through this proof, you discover certain interesting facts about other things that will be helpful, I think, to you. So this is just useful sort of geometric knowledge for all of you to have. Okay, so let me teach you something else, which is a more modern idea, but it's related to this problem. So I'm going to go down again here. I hope it's possible for you to read what I'm talking about. I want you to notice something. So
Mr. Mark, your voice is not clear.
All right. Am I clear now?
Yeah.
Great. So my question is, how many corners does this shape have?
5.
You sure?
Vertex. I heard you. Vertex 1, 2, 3, 4, 5, 6.
No, there's only 4.
Oh, okay.
So there's 1, 2, 3, 4. So there's this is just the back of this thing. Okay. Maybe my picture is not clear. So there is one triangle here, and there are 4 triangles in total. Do you agree?
Yes, I agree.
Yeah, so 4 vertices. So let's just say V, the number of vertices, equals 4. We'll call V the number of vertices. Okay. Now, how many edges do we have? Okay, so these are the edges. This is an edge. There's another edge. There's another edge. There's another edge. How many edges do we have in total?
6.
6 edges, exactly. So E equals 6. And finally, how many faces do we have? These are the faces. How many faces do we have?
4.
Yeah, 4 faces. So we say F equals 4. Okay, that was easy, right? But I want to just teach you the language. So you understand what these things mean now. V equals 4, E equals 6, F equals 4, yeah?
Yes.
Okay, now let's take another shape. By the way, it doesn't have to be regular, right? Let's take a non-regular shape for a second. Non-regular. Let's take the example you came up with, Ian, of the square-based pyramid, right? So let's consider the square-based pyramid. I just want to we want to learn how to count vertices, right? Sorry, I'll make this a bit better. So this is a square-based pyramid. Square pyramid, like the pyramids of Giza, right? So you have 1, 2, 3, 4, 5 vertices. Everyone agree with that?
Yes.
Yeah. How many edges do I have now?
Or 8.
8. Yeah, exactly. 1, 2, 3, 4, 5, 6, 7. I'm missing one. 8. Yeah. And finally, how many faces do I have?
5.
5. Okay. We'll leave that alone. I'll come back to this in a second. We're gonna observe something in a few minutes. Now let's look at the cube. Okay, again, the same question, right? So first of all, vertices. I'm drawing them here. How many vertices do I have?
8.
8. Great. How many edges do I have?
Edges. 16.
Not 16. A little bit less. So you've got a square on the top here. There's 4 edges there. Square on the bottom, 4 edges there, and then you've got the 4 connecting edges. So edges is
12.
12, exactly. Well done. And then finally, faces. It's a cube, so we know this one.
8.
Not 8. Count them.
6.
You got 1 on the top, you got 1 on the bottom, and you got 4 around the side. 6, right, exactly. Great. Making sense?
Yeah.
Let's do one more. of this. I'm going to make something. I'm going to build a little house here, right? So I'm going to make one that's a little bit funny. It's going to have the cube with the square-based pyramid on top. All right, so there's the square-based pyramid, and then we attach the cube underneath. So just so it's clear what shape this is, I'm going to mark everything off. Here are the vertices. So it's kind of like a little house, okay? And here are the edges in green. Sorry, I told you the pen sort of slips on this surface. It's difficult to draw, I'm sorry. You guys try counting as I'm doing this. Okay, so there's my little house, okay? So now, number of vertices. V is?
9.
Yeah, that looks good. Number of edges, E equals. It's a bit harder. So notice I've got 4 on the top coming to that corner. I got 4 on this square. I got 4 vertical ones and I got 4 on the bottom.
16.
16, yeah, well done. And then finally, how many faces? Now, this is a little bit tricky because we just want the outside of the house to be faces, right? So there's the roof. The roof has 4 faces, and there are the walls, 4 faces, and there's 1 on the bottom. So you're going to have 9 faces. Does that make sense? So notice that there is not a face. Yeah? You understand that? You're okay with that, Lean? Yeah?
Yeah, it's all clear.
That yellow one's not a face. Only the outside count as faces, right? Okay, yeah. So we did a bunch of little countings. Now let's go back and observe something, right? On all of these. If you look at the number V, and you minus the number E, and then you add the number F, what do you get? So in this case, it's 4 minus 6 plus 4. And what number is that? What's 4 minus 6 plus 4?
6.
4 minus 6 plus 4 is 2, right? Yeah. 4 and 4 is 8, minus 6 is 2, yeah? What is it in this case? 5 minus 8 plus 5.
Also 2.
Also 2. What is it in this case? 8 minus 12 plus 6.
Also 2.
Also 2. You're beginning to see a pattern here. What is it in this case? 9 minus 16 plus 9. It's also 2, right? Okay.
Yes.
In fact, it will always be 2. Okay. In fact, if you take any regular solid, like not even regular solid, just any solid like that, okay, and you break it up, but you build it out of these polygons, these faces, and the faces don't have to be regular. They can be different sizes. They don't have to be regular, but you build it like this, and you only count the faces on the outside. Okay, you don't count stuff like this in here. You count the faces on the outside, and you work this out: V minus E plus F. So this is V minus E plus F. This will always be 2. This is called Euler's number, or Euler's formula, I should say. Euler's formula. Okay. And you can see this in lots of places. Do any of you play football? No?
Yeah.
Yeah. So have you noticed on traditional old-fashioned footballs, the ball is built out of hexagons and pentagons?
Yeah, that's right.
Yeah, you get a combination of hexagons and pentagons. So it's not regular in the sense we're talking about, okay? So you'll get a hexagon here. I should color code this. So there's the hexagon there, and pentagons as well. It's not regular, okay, but it doesn't matter. You can still think of it as a polyhedron, just a not regular one, built out of faces. And if you count up, you can try it yourself. Go find a football and count. You can try it yourself. If you work out the V minus E plus F, you will get 2 always. Okay. So that's a very famous fact. It's a more modern fact. It was proved maybe 200 years ago, 200 or 300 years ago. But it's true, and it's a very, very useful thing to know. Okay, does that make sense?
Yes.
So now I haven't proved it. I've just told you it's true. So here's what I plan on doing next week. So next time, we're going to do 2 things. One, we're going to prove Euler's equation. I'm going to prove that. And the second thing we're going to do is we're going to prove that there are exactly 5 Platonic solids. No more. Five Platonic solids. Now, as I said to you, the second fact, this fact here is very old. This has been known for thousands of years. The first fact is not as old. This has been known for a couple of 100 years. I'll just say hundreds. Not that many hundreds. Okay. And there are various ways of arguing this. I'm going to actually use the more modern. I'm going to use the first fact to prove the second fact, which seems a bit strange. But I'm not going to do it the way it's you know, this is not the only way it can be done. I'm choosing a way of doing it which I think is nice and teaches you a lot of different tricks and different things. That's the reason I'm doing it this way. So there are other proofs available, and you can go online and find lots of different proofs of this second fact here about the Platonic solids. But I think learning about Euler's equation would be very useful to you. And there's some nice geometric tricks in there that I think you'll appreciate. So I hope that's okay. So we can start this this proof next week and go through this. Is this making sense?
Yes.
Yeah, and this is it. This is interesting. This is useful, I hope.
Yeah, the lessons today was very interesting.
Yeah,
I
mean, at this point, I don't want to just go through Olympiad problems yet, because I think there are lots of things to teach you. I know that some of you are doing the sort of intense training with Taxine, I think his name is, and John. But I think I want to just sort of teach you some interesting mathematics as well that you mightn't have seen before. I think this will be helpful. Is this okay?
Yeah, that is actually helpful.
Okay, great. Okay, so maybe we'll stop today and we'll try again next week. We'll meet again next week. Let me just stop sharing my screen so I can look at you again. Hang on a second. Go back to Zoom. Stop share. So now I'm back. So any questions before I go? How are things going otherwise?
I guess everything was clear. Today's session was like very interesting and fun.
Okay, thank you, Lynn, for that. So you guys you're all on your summer break, is that right?
Yeah, I guess so.
Do you have any fun things planned?
I have to study because this is my last year. Like I'm up to my last year. Yeah. So no fun for this summer break.
No summer. And do you have big exams coming up?
Yeah.
I see. What about the rest of you? Do any of you get any time off? No? Nothing, no response. Okay. Well, I won't stop you. I'll let you go on and enjoy your Friday. So anyway, if you guys want, we can carry on next week. I'll be here. I'm happy to talk more about this. And if you have any questions, you can always share them with me.
Thank you very much.
No problem. No problem. Okay. Take care, everyone. Bye-bye.
Bye.